Out past Neptune, the solar system stops acting like a tidy clock, and starts acting like a case file. Because way out there, hundreds of times farther than Earth is from the Sun, a handful of icy worlds follow orbits that look suspiciously coordinated. Like someone nudged them into place. And if that someone is real, it's not small. We're talking about a hidden object that could be 7 to 17 times the mass of Earth, moving on a stretched, tilted path so huge that one lap around the Sun could take 10,000 years or more, and spending most of that time in darkness, hundreds of astronomical units away. Here's the unsettling question. If something that big can hide in our own solar system, what else is out there that we've never even thought to look for? Astronomers call it Planet 9. Not because we've photographed it, because we haven't. We call it that because the outer solar system keeps leaving patterns behind, the kind you don't get by accident. These distant bodies are trans-Neptunian objects, TNOs. They live in the deep freeze beyond Neptune. And when scientists chart their orbits, some of the most extreme ones don't scatter randomly the way normal debris should. They cluster. They tilt. They line up in ways that make you stop and say, gravity did this. But here's the problem. Gravity doesn't sign its name. It only leaves effects. So the Planet 9 mystery isn't a photo, it's a fingerprint. A gravitational signature written into the outskirts of the solar system over millions of years. Imagine walking into your kitchen and noticing every loose magnet on the fridge is pointing the same direction. You didn't arrange them. No one admits arranging them. Yet the pattern is too consistent to ignore. Something is shaping the field. That's what Planet 9 would be, the unseen field shaping those distant orbits. This story took off when astronomers started finding extreme outliers, objects like Sedna and others with bizarre, detached, highly elongated paths. They're so far away that most of their lives are spent in deep space, only briefly swinging close enough to be detected. In 2016, researchers at Caltech argued a hidden planet was the cleanest explanation, a super-Earth on a long, tilted orbit, slowly sculpting the Kuiper belt over cosmic time. Since then, simulations have narrowed what it might look like, likely several Earth masses, possibly up to around 10 or more, orbiting hundreds of AU away. Except, evidence isn't the same thing as proof. Because astronomy has one unforgiving rule: if you can't detect it, you don't get to call it found. So why can't we just point a telescope and snap a picture? Because distance doesn't just make things smaller. It makes them vanish. A faraway planet gets less sunlight, and then has to send that already weak light back to us. The dimming compounds fast. And that's what makes this so maddening. We can image planets around other stars. We can see galaxies from near the beginning of time. Yet a planet in our own solar system might be hiding in the dark like it's deliberately dodging us. Unless, we've been searching in the wrong kind of light. Before you buy into any Planet 9 found headline, you need one simple scale marker. 1 Australian dollar is the Earth-Sun distance. Neptune sits around 30 Australian dollars. The objects hinting at Planet 9 can live at 200, 300, 500 Australian dollars and beyond. Out there, sunlight is barely a suggestion. Temperatures drop. Motion slows to a crawl. And that's where an old truth becomes useful: planets don't only reflect light, they also give off heat. A tiny amount, but enough to glow faintly in infrared. Which leads to the clever twist: instead of chasing reflected sunlight, look for the planet's own thermal glow. And here's where it gets weird. This hunt doesn't rely on one telescope at one moment. It uses time itself. Researchers went back into the archives, infrared sky maps from decades ago, then compared them to a newer infrared sky map made more than 20 years later. 2 full sky snapshots. Decades apart. If Planet 9 exists, it shouldn't sit still. The older survey is IRAS, the infrared astronomical satellite, which scanned the sky in 1983. The newer one is Akari, launched by Japan, which surveyed the sky in the mid-2000s. By comparing auroras to Akari, researchers searched for a faint source that shifts position at the slow pace you'd expect for a world hundreds of AU away. It's essentially turning the sky into a long-exposure time-lapse. A hidden planet can't hide from motion. But here's the catch. At those distances, Planet 9 wouldn't move like an asteroid. It would creep. That's why the multi-decade gap matters. Over a night, the shift is tiny. Over 20+ years, the shift becomes measurable, enough to separate real mover from fixed background. The search strategy is ruthless and practical. Start with massive infrared catalogs containing millions of detections. Filter by what a Planet 9-like object should do over 23 years. Throw away anything that's clearly a galaxy, a known source, or a bad detection. Then keep only what behaves like a slow-moving object with the right kind of infrared signature. And the reason the orbit shape matters is crucial. Objects move slowest at their farthest point, aphelion. If Planet 9 is real, it likely spends most of its time way out there, moving so slowly it looks almost frozen, which is exactly why we keep missing it. Now, picture what the signal looks like. Don't imagine a gorgeous James Webb portrait. This is not cinematic. This is forensic. It's more like a faint warm smudge in one dataset, and a faint warm smudge in another dataset, offset just enough to suggest it moved. In the example described in the reference approach, the candidate shifts by roughly 47.5 arc-minutes between the surveys, about 1.5 moon-widths across the sky. That sounds big, until you realize it took over 2 decades. But here's the problem. 2 snapshots don't give you an orbit. They give you a lead. Because false positives are everywhere in data like this. A distant galaxy can vary. A detector can glitch. Cosmic rays can fake a source. Even subtle processing differences between missions can produce phantom candidates. That's why the funnel matters. In the method you referenced, the pipeline crushes millions of detections down to a small set of candidates, then to the one that still looks plausible after deeper checks. That one left standing moment is thrilling and dangerous. Because when a signal is this faint, confidence doesn't come from excitement. It comes from repetition. So, did we just find Planet 9? Here's the honest answer, not yet. A candidate is not a discovery, it's a target. The analysis argues the remaining signal is consistent enough to justify follow-up observations. But some experts have pointed out that the implied orbit could be more steeply tilted than classic Planet 9 models usually predict, which raises the possibility that this object is something else. Except that doesn't make the story weaker. It makes it sharper. Because even if it's not Planet 9, it could still be a brand new world we didn't know was there. So what would confirmation actually look like? Not one dramatic image. Confirmation means repeated detections, night to night, month to month, showing consistent motion that fits a stable orbit. It means ruling out background galaxies. It means matching brightness across wavelengths. It means building a track record, not a rumor. And that's exactly why the next phase of this story matters more than any single candidate dot. Because the ultimate Planet 9 machine isn't a one-time telescope. It's a survey that watches the same sky over and over and over. The Vera C. Rubin Observatory in Chile was built for this kind of chase. With its enormous 3.2 gigapixel camera, Rubin is designed to scan huge portions of the sky repeatedly for years, creating something closer to a sky movie than a sky photo album. And that changes the game. Because if Planet 9 is out there, it can't hide from time. Motion will betray it. But let's flip the mystery. What if Rubin watches for years, and nothing fits? Then the solar system is still confessing something, we just misidentified the culprit. One alternative is collective gravity. Instead of one hidden planet, the combined mass of many distant objects could gently shepherd orbits into patterns. Another possibility is ancient history. A passing star early in the sun's life might have tugged the outer solar system, leaving scars we still see today. And then there's the idea that sounds crazy, until you realize serious scientists have discussed it. What if the unseen mass isn't a planet at all? Some researchers have proposed, in principle, a primordial black hole, an object formed in the early universe, could have a planet-like mass while being extraordinarily compact. That's not the mainstream expectation. But it shows you what's at stake. When you chase an invisible gravitational source, the answer might be stranger than the question. Planet 9 isn't just a ninth planet debate. It's a test of how well we actually understand our own neighborhood. If it exists, it means the solar system still has a major member we've never met. If it doesn't, it means the outer solar system is organized by a more complex mechanism than a single hidden world. Either way, the era of guessing is ending. Because Rubin won't just take images, it will build evidence, frame by frame. Somewhere beyond Neptune, something has been shaping the edge of the solar system for a very long time. It might be a super-Earth on a 10,000-year orbit. It might be the combined pull of an unseen population of objects. It might even be something we haven't imagined yet. But we're entering a moment where, we can't see it, stops being an excuse. Because once the sky is monitored night after night, the outer solar system won't be able to keep secrets forever. And when the answer finally shows itself, it won't just add a new dot to the chart. It will change how we understand the entire frontier.